Welcome to the beginning of 5.2 notes, where we're going to use properties of exponents that we should already know to apply them to rational exponents. Now, I think that it probably makes sense to review some of the power properties that you already might know. See if these make some sense to you. If not, I hope that we I can explain them to you. So what I'd like you to do is I'd like you to simply fill out this form and match the different things. So I want an answer for each one of these blanks as well as a letter. So pause the video and see if you can make that happen. All right, so the first thing I'm going to do is go through what these are about. I'm going to start with the easiest one possible, number 4. Number 4 is 8 to the third times 8 to the fourth. 8 to the third times 8 to the fourth is 8 to the seventh, because if you have a's and you multiply by 4a's, then you've got 7a's. And let's see which one that is. That would be product of powers. Product of powers. So I would call that A. All right. Now let's see. The next easiest one would be number 3. A to the third to the fourth is A to the 12th. And that's because if you took A to the third 4 times, A to the third times A to the third times A to the third, we could use the first rule that we just learned, product of powers, to be able to just add 3 plus 3 plus 3 plus 3. In other words, we're just multiplying 3 times 4. Now this is called a power to a power. So we use this one and this one. Power of a product seems like it should be multiplying something before you take a power. Let's see, power of a product must be number 2. If you do AB to the 4th power, that means it's A to the 4th power times B to the 4th power. So that must be C. And negative exponent is the one right above it because it has a negative exponent. So what do negative exponents do? Negative exponents take reciprocals. That's 1 over A to the 2nd power. If you need a little explanation on that, I would go to this kind of example. Let's take a look at the pattern that's going on. If you know that 2 to the first is 2, and 2 to the second is 4, and 2 to the third is 8, because you're multiplying by 2 every time, right? Well, if you're multiplying by 2 to go up, then you're dividing by 2 to get from 8 to 4. And 4 divided by 2 is 2. And 2 divided by 2 is 1. And 1 divided by 2 is 1/2. And 1/2 divided by 2 is 1/4. See, these negative exponents are reciprocals of the ones with the positive power. So 2 to the first is 2. 2 to the negative 1 is the reciprocal of 2. Same thing with 2 to the second power is 4. 2 to the negative 2 is 1/4. It just makes it go upside down. And if you had a number that was had a negative exponent in the denominator, it would be a positive exponent in the numerator. So for instance, if we had 1 over 3 to the negative 2 power, that's the same as positive 3 to the 2 power. So that's the same as 9, another way of looking at it. All right, so let's see what we've got left. I'll pick another color. So wait a second, that means that 0 product rule, or the 0 power rule, the 0 exponent, that's number 7. That must be anything to the 0 power is 1, because I just arbitrarily picked 2 because it's easy, but I could have picked any number. Let's see what we're left with. A to the 6th divided by A to the 2nd is A to the 4th. If A is not 0, because you can't divide by 0, it's a no-no. That would be one of these two that's left. Quotient of powers or power of a quotient. Quotient of powers or power of a quotient. Well, power of a quotient is like power of a product, and that was the one where we took the product first. So quotient must be first on that one. So quotient of powers is F. That's this one. Whereas the last one must be a power of a quotient. The quotient is A over B, the division problem, and we're taking the power of it. So we're doing A to the third divided by B to the third. Each A and B get to the third power in that type of problem. So these are the basic properties. And this, if you need some practice on that, that would probably be a great idea to go over basic properties of exponents. But these are the ones you need to know to be able to be successful when you're doing the same exact thing with rationals, rational exponents. So for instance, we have to apply those same rules for these kind of things. We're not expecting some kind of answer that would be a decimal or something like that. For these, we think you should be able to do it without a calculator, unless you're doing the calculator to do the calculations of the exponents. So let's see what's happening. I'll do the first one or two, and you can try it. Or you can pause here and try them on your own first. So the first one, I've got two numbers with the same base. So I'm going to use the product rule that says when I'm multiplying two numbers with the same base, I'm adding the exponents. So I'm going to add 2/3 and 4/3. 2/3 plus 4/3 is 6/3, which is 6/3 is 2. So the answer to this first one is 25. Now, if you just got a calculator out and did it that way, that'll be fine, but you probably won't be able to pass a test if you do it that way, because we could use just letters on that, and you have to do it that way. So 3 to the 1/5 times 3 to the 4/5. Well, we've already got a common denominator, so I just have to add those things. That would be 3 to the 5/5. That's supposed to be a 5. 5 over 5 is 1, so that's 3. What rule is this one? Power to a power. Power to a power, we multiply. So 2/3 times 3 is 2. So the answer is 16. This one as well. 10 to the 1/2 to the 4th power. The power to a power, we multiply. 1/2 of 4 is 2. So that's 100. Over here, we're using the division rule. The quotient property says if we're multiplying, when we multiply, we add the exponents. If we divide, we're subtracting the exponents. So 5/2 minus 1/2 is 4/2. 4/2, of course, is 2. So that's 64. They don't always turn out nice and pretty like this. And this one over here, I'm going to suggest that we subtract. We could either do it this way. We could say 2/3 minus 5/3 is negative 3/3. So this is 7 to the negative 1, which is 1 over 7. But it would be a whole lot easier to subtract from the bigger number. 5/3 minus 2/3 means that there's more 7s in the denominator. So we have 1 over 7 to the 3/3, which is 1 over 7. Of course, it works out the same. I would always subtract using the larger number and put the exponent, or put the base wherever it belongs. So if you have more 7s in the denominator, put it in the denominator. If they're more in the numerator, like the first one we did, you put it in the numerator. All right. So let's see what these are. Are these the same things? Well, yeah, they are, because remember, we can convert these between these two forms without any issue. So you might want to pause and try these. Either you can convert them or you can do them in this form because they're following the same rules. All right, so let's see. The square root of 3 times square root of 12. They're both under the square root, so I can multiply them together. Square root of 36 is 6. I suppose in this chapter we need to say plus and minus 6, but nobody's never going to do that. This one here, the third root of 5 and the third root of 25. Now I'm going to show you two different ways of doing this one. I would say that that's equal to the third root of 125, which is 5. 5 to the third power is 125. Or you could instead say, well, you know, the third root of 5 is fine. The third root of 25, that's the same as the third root of 5 times the third root of 5. Now, when we had square roots, like the square root of 36, the reason why the square root of 36 is 6 is because there's a pair of 6s, right? Because square roots, we need 2 of the same thing. If we're trying to do the same thing with cube roots, we need 3 of the same thing. So the third root of 5 times the third root of 5 times the third root of 5 is 5. In other words, the third root of 5 to the third is 5 to the 3/3, or 5. Just like over here, this would be the same as 6 squared, 6 to the 2 over 2. Well, 6 to the 2 over 2 is 6 to the first power. So you need 2 of those because the denominator is 2. You need 3 of these because the denominator is 3. In the next one, you need 4 of them because the denominator is 4. So you could multiply the 27 and 3 together to get the cube root, or the fourth root of 81, which would be plus and minus 2. Right? Or plus and minus 3, so 3 to the 4th power is 81. Or you could break down that 27 and say, well, that's 9 times 3, and this is 3 times 3. There are 4 3's. So the fourth root of 3 to the 4th is plus and minus 3. I'm doing plus and minus because it's an even root. Try the next ones. All right, so let's see. 98 divided by 2 is 49, because they're both underneath the radical. This one over here, I guess I could divide it out and say 4 goes in there, I don't know, 256 times, I guess. And I know that 16 times 16 is 256. So I'm going to guess that this one is 1/4. I'll do plus and minus since it's an even root. 4 to the 4th power is 256, since 16 squared is 256. And this one here, 625 divided by 5 is 125. The third root of 125 is 5. So I've given you a couple different ways of doing those problems. All right, let's see what's going on. What's next? So this is a summary of the rules we just talked about: product rule, power of a power, power of a product, and so forth. This is how it relates to the exponents. If you want to pause and take a picture of that, that's fine. It's in the textbook. Here's something else from the textbook, and it's just examples of these things. And this is the way they did it. It said, well, okay, if I'm doing 7 to the 1/4 times 7 to the 1/2, I can't add them as easily. I've got to add those two exponents because it's power times a power, right? So two numbers with the same base. But adding 1/4 and 1/2, you have to get a common denominator and all that. That's where it's 3/4. The next one here, 6 to the 1/2 and 4 to the 1/3, they don't have the same fraction, right? This is a 2 and this is a 3, and they don't have the same base. Well, I either need the same base or the same exponent to be able to make these things work, and this is not happening. So you'll notice that in this problem, the 6 to the 1/2, I wouldn't do it with all these steps myself, but it shows you how it's doing it. It would say, well, 6 to the 1/2 to the second power is 6 to the first, and 4 to the 1/3 to the second power is 4 to the 2/3. So they show all little steps to get there, but I don't think most people are going to do, especially this step. It seems like it's overly hard. But you can't combine these original problems. You can't combine the 6 and the 4 because they are two different exponents. If they were the same exponent like these, we could combine them, or the same base, right? If they're the same base or they're the same exponent, but not in this case. So this 4 to the 5th power and 3 to the 5th power, you see, now I can use a rule to get those together because they're both to the 5th power. So it's the same as 12 to the 5th power to the -1/5 power. That was on the outside. So all we're doing is multiplying 5 times -1/5. So that's -1, which is the same as the reciprocal of 12. So you can study those examples before you try your own. Try these 4, and then we'll go over them. Okay, let's try this one. Now these have the same base, which means I can combine their numerators. So I need 3/4 plus 1/2. 3/4 plus 1/2 is like 3/4 plus 2/4. So that's 2 to the 5/4. All right, and this have the same base as well. So since they have the same base, I can subtract the exponents. 3 has no exponent, so it's the same as 4/4 or 1. 4/4 minus 1/4 would be 3/4. There you go. This one has the same base, or the same exponent, so we can divide the 20 and the 5. And then, so 20 divided by 5 is 4 to the 1/2. Of course, 4 to the 1/2 might be easier to say as 2 to the 3rd power, because it's the square root of 4. And 2 to the 3rd power is 8. The last one, neither the base nor the exponent are alike, so we have to treat them separately. A 1/3 to the 3rd power means multiply those guys together. 1/3 times 3 is just 1. 1/4 times 3 is 3/4. So that's all I can do. 5 times 7 to the 3/4. That's it. Clear as mud, I'm sure. So we can take a look at these radical properties, but I don't think that they're any different from the properties that we already have. It basically says if you have two things that are a radical, you can separate them out into two different radicals. Or like 4 and 2 are both under the cube root, so you can multiply them together or you can divide them, whatever. And a over b, if they're both under the radical, they're the same as having them on the top and bottom. So I don't think that's a huge revelation.